So today we're going to start chapter 9, which is on differential multistage amplifiers. We started taking a look in chapter 8, building blocks for op-amps, the current mirrors and current steering techniques of developing bias, and also the basic gain cell, which is internal to the amplifier. And then in this chapter, we're going to take a look at a very important block, which is the differential input stage. And as you know, an op-amp is a differential input device. You have a negative input and a positive input. So the question is, what do these signals go into? What is the circuit that these signals feed, and how we convert that differential input to a single-ended input that we can then use to drive the basic gain cell, and go downstream from there to start putting together like a multi-stage amplifier. Okay, so that's what this chapter is about. And then to start, I want to start by commenting on figures 9.1 and 9.2, which gives you the basic topology of the differential pair. Okay, so this is made of two transistors that are biased with they are in common source configuration, and they are biased with drain loads, and the inputs go into the gates of the transistors, and that makes the basic differential pair, okay, at a very, very basic level, okay. And as we go through the analysis, the reason I show this, and you should refer to these figures, is because the quantities, for example, the quantities that are in blue are the ones that we're going to be referring to in the analysis later on, okay? And then here in figure 9.2, there is a little bit more elaboration on the quantity. So we'll go through that in detail. So what we're going to do next is start analyzing this topology for the basic differential input amplifier, the differential pair. So for that, I'm going to switch to my pad then, and we're going to start working through that. Can everybody see the canvas?
Yes.
I'm seeing a blank screen. Oh, there it is.
So you got it? It's showing?
Yes.
All right, thank you. All right, so we're going to start talking about the MOS differential pair. So we looked at, this is based on figures 1.9, I mean 9.1 and 9.2. And the first thing that we're going to define is the gate voltages. So we're going to call that, there is a transistor 1 and a transistor 2. And we're going to define that as the differential input voltage, so that's VID, and then we're going to introduce some common quantity to both inputs. So we're going to say that the absolute voltage at the gate of transistor 1 is going to be some common voltage, that's VCM, and then the actual differential input between both the voltages at both gates, we're going to assign half of that differential input or that differential quantity to the gate of transistor 1. Therefore, the voltage at the gate of transistor 2, we're going to define as that common voltage minus the differential voltage divided by 2. So in essence, if you subtract VG1 from VG2, take the absolute value, it gives you the differential voltage, okay? But we have to realize that there is this common voltage and ideally be the same, and we're going to look at later what the non-idealities of not having a perfect common voltage. But for now, let's say that there is this common characteristic to the differential pair, where we can say that that common voltage is also, if you solve and use the two equations before, is VG1 plus VG2 divided by 2. So that gives you like an average. So we can say that that common voltage is the same because it's an average of the absolute value of the voltages at the gates. And then the actual differential input, as I said, we get it if we take the absolute value of the difference of the value voltages of at the gates. So it really doesn't matter which one we subtract from which. So that's what we would define as our differential input.
Dr. Hernandez?
Yes.
Keith's asking if you could let him in.
All right, done. So let's continue. Now, first of interest is considering if we say that the voltage at the gate are going to be the same and are going to be that common voltage. So obviously then our differential input is 0. What happens there? Furthermore, when we build this circuit, we're going to strive for Q1 for the transistors to be matched. So that means that they have the same electrical width of the channel, essentially. And if that's the case, and if you go back to the topology, the drain currents are going to be the same. The transistors are matched, and they're going to be the same, each one as half of the total bias current at the sources. That bias current that shows tied to the sources of the transistors. Also, the voltage at the source is going to be that common voltage, which is showing at the gate, minus the VGS of the transistor, which is the same for both of them because they're matched. Then if we, based on that, write the drain current equations for the transistors, which again is the same, we get that the drain current equation, going back to our drain current equation, and these are N channels, only one WL ratio because the transistors are matched. So this holds for both transistors. So that's our drain equation. And also the overdrive voltage for both transistors. So it's is Saad having problems seeing the screen?
Yeah, I can't see anything for some reason.
And do you wanna I'm going to put you in the waiting room and admit you again, okay? To see that fixes it. Does that work?
Okay, yeah, you can try that, yeah.
Let's try that.
Okay.
So let's wait for Saad, and also Justin is joining.
Okay, I can see it now.
All right, excellent.
Thank you. Thank you.
No problem. All right, so we had formulated the drain current equation for both transistors, given the case that we're looking at. And then the other thing that we can say is that the overdrive voltage, again, for both transistors, is going to be the gate to source voltage minus the threshold voltage. And then if we use that, we can write, actually, let me just clear this. We can write that, and that's the drain current, so that's still the drain current, just substituting for the overdrive voltage there. But the overdrive voltage is an important quantity because it tells us how much gate to source voltage we have to apply above the threshold to get the transistors operational. So that's why we want to solve this equation for the overdrive voltage, okay? And that gives us this expression, okay? If the transistors are matched, then the voltage at the drains are going to be the same. That's also the case. So VD1 is equal to VD2, and then that's going to be the supply voltage minus the current through the drain for each transistor, which is I/2, times the drain resistance or the load. Okay. And also another observation is that since the output is taken differentially from both drains, so we can define our output as the difference of voltage between both drains. That's going to be 0 because VD1 is equal to VD2. So I have that right here, so I don't have to write that again. And we expect that because the case that we're looking at is that the differential input is 0. So we have shown that if we get a differential input of 0, we get a differential output of 0. So that makes sense. That's an important, it's telling us that the differential pair is behaving as a differential amplifier. Now let's look at what some boundaries that are of interest for this circuit. And the first one is for the input, what is the maximum common voltage that we can have? And that is going to be the threshold plus the drain voltage. That's the maximum that we can have if we want to be in the linear region, which is the threshold voltage, the supply, minus that voltage that is developed across the drain resistor. So this is the drain current times the drain resistor. The minimum common voltage that we can have is going to be the negative supply and plus the common voltage at the source, because the sources are tied together, plus the threshold, plus the overdrive voltage. So that is the minimum that we need to be in linear operation. So that gives us some sense of what's going on. So let's look at another figure to continue before we continue. Another figure that is important. And that's the same figure, but now we have the gate of transistor 2 grounded, and we are applying all our differential voltage at the gate of transistor 1. And this is all the differential voltage because the input voltage at the gate of transistor 1 minus the input voltage at the gate of transistor 2 is the voltage at the gate of transistor 1, because we have the gate tied to ground at transistor 2. So that is an important, we're going to make some important observations based on that. So the question related to that figure or that case is, what is VGS1, where we're applying VGS1 for all the current to flow through transistor 1. When essentially transistor 2 is off, or when we could even say when transistor 2 is coming out of being off. So VGS2 is equal to the threshold voltage. So in that case, we know what the current is. We said that that's all the current. So the circuit is no longer balanced. All the current is flowing through transistor 1, and we apply the drain current equation. And we get this expression, and we solve for VGS1, because we wanted to know what that is, right? If we solve for VGS1, we get that that voltage is VT plus 2 times the current divided by K prime times the geometry. Which is, conveniently, so the threshold plus some nice constant, the square root of 2 times the overdrive voltage. So if we have that overdrive voltage, applied to both transistors, then we get back to the balance state. So that's the maximum, but as we start increasing the overdrive voltage for transistor 2 and reduce the overdrive voltage for transistor 1, we get back to the balance state. Essentially, what that says is that then both drain currents are going to be the same, and the differential pair is going to be balanced. Then the question is, what is the maximum differential input voltage that we can have in the linear region, so we can figure out what is the dynamic range of this differential amplifier? So what is VID max? And if we go back to the topology, that is going to be VGS1 plus the voltage at the source, which is the threshold, plus that overdrive voltage minus the threshold. So the maximum is nicely the overdrive voltage as given by the previous expression. So we can say that the range of the differential voltage is between plus or minus the square root of 2 times the overdrive voltage, and the overdrive voltage is, remember, is here. I'm going to write it here. that. So we know the W and the L because we know the geometry of the transistors. The K prime is given by the process. Remember the mobility, the capacity of the oxide and things like that. And then this is our bias current, how we want to bias the differential pair. And then we come up with this, and that gives us a range of differential voltage. Conversely, from a system perspective, you will start with what range do you want for your differential input? That's really where you start. And from that, you set your overdrive voltage, and then it gives you a trade-off between the current that you want to have, depending how much low power you want to be, and all the considerations like speed and things like that, and how big your transistors need to be. So from a design perspective, you go from system to here to design equation here. So that is the observations on the range for the differential input. Now let's look at the large signal operation, okay? And we're going to define, because we have to define which one is the positive input and which one is the negative input. We're going to define that the differential voltage is VG1 minus VG2. So meaning that this is your positive input and this is your negative input. We're going to make two simplifying assumptions that are important just to keep things simple. And if you recall, and I said that the chapter on the fundamentals of the MOS transistor, chapter 5, is important because some of this terminology is coming from there. And I did say that you should have reviewed that chapter so you know what these quantities are. We're going to assume, to make things simple, that the channel length modulation, lambda, is 0, and that the early voltage is infinite, okay? So that reduces our dependency in the, or our changes in the output resistance of the transistor. And also, for the consideration of this analysis, Q1 and Q2, what we're talking about is Q1 and Q2 operating in the linear region. I've been saying it, but I'm writing it now formally. Okay, so now let's go back to a figure 9.5, and see this figure that is related to this topic. And this is what we're going to be using to derive the transfer characteristic of the drain currents versus the differential input voltage as we have defined it. Okay, that's the quantities of interest there. All right, let's keep going with analysis. So the quantities of interest are the drain current for transistor 1. So again, we just write our drain current equation. And for transistor 2, we have the corresponding drain current equation. So what I can do is solve, because I want to find out how these currents relate to the differential input voltage. And I know that my output voltage is going to be related to those currents because they're going to be a voltage developed across the load due to these currents. So I can write that the square root of the current in the drain current of transistor 1 is equal to the square root of this quantity That's just taking the square root of both sides of this equation. And then similarly, if I do the same thing for the second equation, I get this expression. So what I'm going to do with this too, okay, is the following. I'm going to subtract one equation from the other, and I'm going to substitute so this is going to be my differential input voltage. So if I do that, I get so this is what I get. But I can also recognize that, just to simplify things, I can recognize that the sum at any time of the drain currents is going to be equal to my bias current. So really the way that this differential pair is operating is that the current, the sum of the currents of the drain of both transistors is always constant. And the way that it's working is by the input creating unbalance, the differential input creating unbalance in these currents and developing a differential output. So that is the effect of that differential amplification. But this is a constant. If that's the case, then I can write this expression as well. And then also, the current that drain to the drain of transistor 2 is just the bias current minus the current at the drain of transistor 1. So if we apply this, then we can solve that previous equation that I had there. So this one, I'm gonna write it again here. So this one, so clearly this is a quadratic equation on the differential input voltage. And if I solve this quadratic equation and take the positive result, which is the only one that is physically meaningful, and so solve quadratic, take result, positive result, and that is only one physically meaningful. And the reason that is because the drain current in transistor 1 in this case is going to be greater than half of the bias current. So we are putting a positive differential voltage in. So if that is what we're working with the positive differential voltage, input differential voltage, that means that the drain current in transistor 1 is going to be higher than half the bias current. The result of all that, so what is the result? Is that the current, the drain current for transistor 1 is that half of the bias plus whatever offset we are creating by the input, by applying a positive differential input or more voltage to the gate of transistor 1, and that is going to be given by this constant. So this relates the current to the input differential voltage. And in general, I can say that the drain currents have these expressions. So having change anything by introducing these terms. So bear with me. And also for transistor 2, if I'm increasing the current in the drain of transistor 1, I must be reducing the current in the drain of transistor 2 by the same amount. Like so. So at any point in any of the equations that we have written, we can check that that if the differential voltage is 0, then we're going to have a balanced differential pair. And it's going to be half the current, half the bias current is going to be running through the through each of the drains of each transistor, which is which corresponds to having the same VGS for each transistor, because again, the differential voltage is 0, so the gate voltages are the same. And the final result that gets yielded is this. Half the bias current which is equal, this is just the draining, the drain current equation, and that is equal to our overdrive voltage. And we can use this to size the transistors. And I was talking about the how we use this to design the differential pair. And the way that you use it is that you can use this in this fashion. We get this relationship. So now we have some quantities that we can get from our system, and we have this that is a given of the process to actually, draw the transistor, which is the only thing that we have control over. The only thing we have control over is that W. But the other quantities come from, it's important, and perhaps one of the most important things that a designer needs to know how to do is to take the system specification and derive translate that to design constraint. This is a design constraint. The W is a design parameter, which is actually going to affect what you actually do physically, the width of the transistor or the width of the channel. But it comes from that analysis and interpretation. So if we use this, then I can get back to general expressions for my drain currents. So that's for transistor 1, and similarly for transistor 2, half the bias minus a similar expression. And the nice thing about this is that these IDs, drain currents, let me clear this. So the nice thing about those equations is that are functions of the input, the differential input voltage. And then if I want to have a design framework, I can use these functions to obtain normalized relationships. So normalizing the drain current to the bias current, and also normalizing the input differential voltage to the overdrive voltage. So that gives me like a general framework of design. It also, those equations also, those functions can also be used to make some observations. For example, if I have a very small differential input voltage, say much smaller than twice the overdrive voltage, then if you go back to the equations, if this is the case, some terms can be ignored or drop off. So if I have that situation, I have this. So by making that, which I could make that a constraint, that my input differential voltage has to be very small, or I can work with very small differential input voltages that are much smaller than twice the overdrive voltage, I get rid of the nonlinear terms in the previous relationships, and I get these two nice and most important linear relationships. So now I have linear relationships of the drain currents that are going to develop my output voltage, my differential output voltage, versus my differential input voltage. That's a very important result, and it works together with the fact that I'm going to have huge gains as I put together this operational amplifier. So I actually do want to work with very small input differential voltages. And since you have been working with op amps at a macro level, using it as a device, you do know that if you want to be in the linear region, you want the voltages, the differential inputs at the positive and negative inputs of the op amp to be very close. That's when the op amp is linear. And that's where the virtual short characteristic of the op amp from a model perspective comes in. So all this starts working together. And hopefully you can start appreciating and understanding why op amps at a macro level from the outside, if you're using it, behaves and operates the way that it does. And here is one part of that we want the differential input voltage. If we have a very small differential input voltage, that's when we have linear relationships. So let's look at a couple of figures related to this. So go back to and show figure 9.6. And here you can see those normalized curves. Here we have drain current normalized to the bias current, okay? And the differential input voltage normalized to the overdrive voltage. And the limits are plus or minus about the square root of 2. Because we said that we already showed that is the useful linear range for the differential input voltage. So everything is coming together. So you're going to operate somewhere along these curves. So here you can see the transfer, the actual transfer characteristic of the drain normalized to the bias current for a specific differential inputs in millivolts, very small, and how your input range varies for different overdrive voltages. Again, very small, but still, this voltage is the differential input voltage. You can see the linear region for each case. And what this shows is that the higher your overdrive voltage, you extend the dynamic input range of your input and also that linear operation. So that is what we call the large signal model. And there is only one more relationship that I want to write, but I'll do that after showing something that is a precursor to the next discussion, which is about the small signal operation. So here, we're going to look at the small signal operation, and we're going to be, so this is the figure of reference of what we're going to be discussing. And we're going to be using, of course, the model, the small signal model of the transistors, and see what happens. Again, if you remember when we went through the models, we're using for these T models that are more convenient than the pi models for a small signal. So the next discussion, which is going to be in the small signal analysis case, relates to this figure 9.8 of the book. So we're looking at that. So let me stop sharing. So the last thing that I wanted before leaving the large signal discussion is that I can define a differential current. Okay, I can define a differential current by taking the differences of the drain currents, and which I had expressions for before I went to the figure, and my canvas erased. But if you take the difference, you're going to see that I can define a differential current that is going to be the bias current divided by the overdrive voltage times the input differential voltage divided by 2. So there is the differential current is a proportional. There is a proportion formed by half the differential input voltage to the overdrive voltage. All right. So let's do a small signal operation based on figure 9.8 that I showed you. And we're going to recall what our gate voltages are. So that hasn't changed. It's that common voltage that we defined at the beginning, plus 1/2 the differential input for transistor 1, and for transistor 2, the negative input, we have the common voltage minus 1/2. Now remember what GM is. Remember what the transconductance is. That is 2 times the drain current divided by the overdrive voltage. But since the drain current, when the differential pair is balanced, is for each transistor is the bias current divided by 2. The GM, when the transistor, the pair is balanced, is the bias current divided by the overdrive voltage. And then I can start looking at my output voltages. So let's look at the output voltages now that we have the small signal currents. Remember that is the GM times VGS. So I can say that for transistor 1, my output voltage, the one that is developed across the load at the drain, is minus GM. And by the way, these are inverting amplifiers. So these are going to be, you're going to have that minus GM. So the slope, the transfer curve is going to have a negative slope. So that is my VGS. And I got the current that is flowing through the drain resistance. And that's going to develop my output voltage for transistor 1. And then similarly for transistor 2. Now, the VGS is the way that we have defined the VGS and the differential input is such that the voltage at the drain of transistor 2 is going to have a positive sign because it's going to be negative and it's going to get a positive sign from the negative that we normally get at the drain of a common source. So that's going to be plus GM and I can look at the proportion of each of these output voltages in relationship to the overall differential input voltage, which is going to be my voltage gain. So for transistor 1, my voltage gain, the output voltage in relationship to the differential input voltage is going to be then minus 1/2 GM RD, and similarly, is going to be plus 1/2 GMRD. Then I can start looking at what is my differential gain. Remember that these are differential voltage amplifiers. So I have a differential input. I'm going to have a defined differential output by looking at the difference of VO1 and VO2, looking at the difference of those voltages at those drains. So I can start looking at my differential gain, which is really what I want to, the purpose of this. The purpose of this differential pair is to be a differential voltage amplifier, which we're going to have to convert them to single-ended, but we'll look at that later. So I can look at what is my differential gain. And I'm going to define that as the differential output voltage divided by the differential input voltage. And I'm going to define that further as if I have my, since I have negative gain for each of the transistors, and I define the input 1 minus 2, the input at transistor 1 minus the input at transistor 2 as my differential input. For the output, I'm going to do the opposite. I'm going to define my differential output as the output of transistor 2 at the drain minus the output at transistor 1. Okay? And if I use the expressions that I had for output voltage 2 divided by the differential before, so essentially this, and I wrote expressions for this two before, I get this very nice result, very elegant, that the differential pair has a gain similar to a transistor. So it's a differential pair, but it behaves as a transistor because the gain, the differential gain, is GM times RD. That is what of a single transistor common source amplifier is, except that it's negative. But in the case of the way that we have defined the inputs and outputs, we have a positive gain. Even though by themselves, each transistor has a negative gain, okay? That's what I was trying to say before. And then if we wanted to include the effects of the output resistance of the transistors, then this could be expanded that just like for the single transistor common source, this can be expanded to GM times RD in parallel with the output resistance of the transistor. Just remember that even though we've been talking about this RD and the schematics have a resistor, in reality, it's very important to keep in mind that RD is really a current source load. It's not a real resistor. It's a current source load that is made out of current steering type outputs and current mirrors and things like that that we discussed in the previous chapter. So now you start seeing how we use that. To put that further in context, let's look at figure 912. Let's look at figure 912. Okay, and here you can see dynamic. We call also this. We also call this dynamic loads or current source loads that are biased from current mirrors. So it would look like this. These are your RDs, Q3 and Q4. Okay. And then when I go back, I'm going to just write the differential gain taking into account the fact that these are transistors and RD is not really an RD. But then I'm going to talk about an improvement on the differential pair because we saw how the technique of cascoding can improve the gain of our gain cells. And then the question is, why don't we do the same for the differential pair? And in fact, that's what we want to talk about next, which is cascoding the differential pair. So this is how it's going to look at. We have the loads. Remember, we ended up with a differential, with a gain cell that was 4 transistors for a common source with a cascoded pair, and then the load also cascoded to improve the gain without detriment to the output resistance. So next we're going to talk about that technique in the context of the differential pair. So the figure of interest is going to be this one, where transistors 7 and 5 are a dynamic load for the cascode pair transistors Q3 and Q1. that are essentially doing the amplification. And then on the other side, the negative input side, then we have transistors 8 and 6 making a cascoded pair for the cascode amplification pair of transistors Q4 and Q2. So, and since it's balanced, we can actually just, and since it's symmetrical, we can just analyze 1/2, and the result is going to be the same for the other half. So that's what we're going to talk about next. I just want to minimize switching a lot between the screen and the pad, but that's what we're going to talk about next. All right, so we're going to talk about the cascode differential pair, but the last thing that I wanted to write, given the fact that we don't really have an RD, is that we have that before we go into cascoding, when we take into account the dynamic load for the differential pair, what we really have is the output resistances of the transistors, and this refers to the figure 912. The output resistance for transistor 1 in parallel with the output resistance of transistor 3. That also can be written in terms of the other half which is the GM of transistor 2 times the parallel combination of the output resistances of transistors 2 and 4. All right. So now let's look at that cascode improvement. So that this is the cascode differential amplifier. Okay. And what we, if you go back to the figure, for an amplifier of this nature, which gain is dependent on the output resistance that is seen at the node where the output voltage is taken. So that's the kind of the drawback of the common source topology, because the fundamental of this is it's a common source. Transistors are operated as common sources. Amplifier is the output resistances. So this is very important because again the gain depends on it. So if you go back to figure 913 and we look at the output resistance, we can define, we see that we have the loads as P channels and the amplification as N channels. So those are the 4 transistors at the bottom of the circuit. We can define an output resistance due to the N channels or the N network, and that's going to be very similar results that we got before. GM3 times R03 times R01. And then the output resistance due to the P network is going to be GM5. And these numbers refer to the transistors at that figure, okay? You have to correlate or relate it to the figure 913, the one we just saw. And That's going to be times the output resistance of transistor 5 times the output resistance of transistor 7. Similarly, so this is looking into the if we look at the other half, okay, we could also write, I guess I'll try to do it smaller, but this is looking at 1/2, so 1/2, and we can look at the other half and get the same relationship. So we can say that on that other half, the output resistance due to the network is GM4. GM4 times the output resistance of transistor 4 times the output resistance of transistor 2. And for the P network is GM6 times the output resistance of transistor 6 times the output resistance of transistor 8. So it doesn't, I mean, it's the same thing. Remember that all transistors are matched. If you go across, each of the transistors are matched. And we can also see that the differential gain, according to each half, is the same as well. So this relies heavily on what we saw in the previous chapter when we were looking at the cascoding of the basic gain cell. It's the same thing. It's like two basic gain cells connected in a differential pair configuration. So all these design techniques are sort of evolutionary, taking one step at a time, one improvement at a time from something that we have seen before. So we can write the differential gain for the cascode case at the node, at the output node, for 1/2 of the circuit is going to be the output resistance that you see going up into the, or going down into the N-channel network, and in parallel with the output resistance that you see up going into the P-channel network. With reference to the GM of the transistor 1, which is actually doing the amplification. Okay? Remember that the transistor on top of transistor 1 is doing the impedance conversion. So you don't get the degradation of the gain because of the output resistance of the dynamic load. And then the cascoding of the dynamic load is doing its part as well as an improvement. So that's basically what we looked at in chapter 8. And now we're just putting two of those legs of 4 transistors each as a differential pair. So this is for 1/2. So this is for 1/2. And then if we want to just write it in terms of the other half, we can do that, and we get the same the same differential gain. So this would be the half that was on the left, and the one that I'm writing now is the one that is on the right. So again, because of that differential pair of cascode configurations is symmetrical. So making heavy use of what we looked at in the last chapter to come up with this result, okay? So next thing that I want to talk about is common mode rejection. If I have a differential amplifier, what I want to amplify is the differential input. But this differential input is riding on a common mode voltage that I have defined. And if there are fluctuations in this common mode voltage, I don't want to see it reflected at the output. It's common. And my differential pair amplifier is supposed to be amplifying differences. So if the common mode changes or the common mode voltage changes, that should not affect the output at all. But in reality, that doesn't happen. There is some fluctuation. And how good my differential amplifier can be immune or not be susceptible to variations in the common mode voltage is what we call a very important metric for an op-amp, which is the common mode rejection. I don't want to amplify voltages that are common to both terminals. And this is very important and very nice to have, because you can imagine that if you have noise in the system and you assume that the noise is common to everywhere, then you can have a high noise environment. And if your amplifier has a good common mode rejection, that noise is not going to be amplified. It's going to be rejected because it's common mode. So that is a very nice characteristic overall of differential amplifiers in a large, a very nice attribute of differential signaling in general, okay? So that's why you see that high speed signaling is done differentially. So because if you have good common mode rejection, then your common mode noise is not going to affect and degrade the signaling. So just to explore that a little bit more, let's look at figure 924. Okay, and look at a small signal analysis of, for simplicity, you could do the analysis on the Cascode, okay, but you have a lot more. The analysis would be more cumbersome because you have more elements there, but the analysis is not less valid if you just do it in a two-transistor differential pair, because the result is going to apply even to the Cascode differential amplifier. So this 9.24 is what we're going to rely on for the next analysis, in which we're going to look at the common mode rejection of the differential pair. So while we're going to this, if you can be looking at this figure, it's going to be helpful, okay? So let me go back to the pad. And let's talk about common mode rejection. The first thing that we're going to do is to define a small signal common mode input voltage. So we're going to say that we have an input voltage that is common mode. And if you go back to the figure, okay, where we had a source resistance as an abstraction for that biasing network at the source, of the pair, that is going to be equal to a current, and this small signal, also look at the small signal topology, times 2i as defined in the figure, times RSS. So these are elements of the figure that we just looked at. Then the next thing that I can do is solve for the current that is due to this common mode input voltage. So from this equation here, that current is the common mode input voltage divided by 1 over GM plus 2 RSS, that resistance seen at the sources. But this current is also part of the drain currents. So that is the current through the drains. So I can write that for output 1, which is the same as output 2, because that's what I want doing a common mode condition, that there are no differences in the output, so my output differential output voltage is 0, regardless of the input common mode voltage. That's the whole point, is going back to the abstraction of RD for dynamic loads times the current. And then the current I derived here. So now I'm relating that current to the output. Obviously, just looking at one half of the circuit. So in this case, the would be the right. I'm sorry, the left half. So now that I have the current and a relationship to the output voltage, and I know that the output voltages are the same, I can write that output 1 is equal to output 2, and that is equal to minus RD 1 over GM over here. And now I have a relationship of the output to the common mode input voltage. So I can look at this and say, what does it take for that output over? So what does it take for the change of the output? Because rejection means that the voltage is going to be small if in relationship to the input common voltage is going to be, or the changes of it, so it's going to be immune to the changes of the common mode voltage. So I can write that the output from this expression over here so I'm trying to see the gain. Essentially, what is the gain of each output voltage due to that common mode voltage? What is the change? And because the GM tends to be large related to RD and RSS, then this is about minus RD divided by 2 RSS. And also, so what the observation here is that this factor is much larger than 1 over GM, because GM tends to be large. So we see what the actual gain, the common mode gains are. These are not differential gains, these are common mode gains for each of the outputs are, and it's this expression over here, and it's negative because each half by itself is a negative amplifier, but still they are the same. So our differential output is still 0. So what this shows is that for any type of common mode voltage, I'm going to have a finite individual gain due to that voltage at each of the outputs, but the differential, the difference, is still going to be 0 for any type of common mode voltage. That is only, so the key here, because RSS, if you go back to the diagram, RSS is common at the sources of the transistors. But even though we have assumed that RD is the same for each of the transistors, they are different devices. They are physically two different dynamic loads. And the idea is that we need to match them because we do want them to be the same to help with our common mode rejection and the whole idea that the pair is matched. But in reality, that's not the case. So I need to investigate what are the effects of not being able to match the RDs. So remember, we have the two RDs here, and I have my transistors here, right? And then here is my RSS. But here we have an RD2 and an RD1. I've been assuming that these two are the same, but they are not. When I write this expression, I'm assuming that there is only one value of RD, but they're not. So I have to investigate the mismatch. And I think we're gonna do that next time because we're running out of time today, and I don't think that we can finish. So we're going to stop here.